that we measure needs a system of units, and therefore there are going to be some amount of errors that are going to creep in. Howsoever good the measurement is, howsoever good the apparatus is, there is going to be some amount of error that's going to be involved. If the error is small, we are very, very close to accuracy. If not, we are far apart from the accuracy. So let's try to understand about how much is the error involved in the measurement, broadly speaking, of length and time in this particular part. So now we move on to the next topic, that is errors and measurements. Every measurement that we do is not foolproof. There are going to be some errors that will definitely be involved in it. So what are the errors that are involved? So let's try to understand that in this topic, errors and measurement. First thing, what is an accurate measurement? Accurate measurement, if we are saying that something is, let's say, 1 meter, then it should be as close to 1 meter, the standard 1 meter, as possible. So that is what is going to be an accurate measurement. No measurement, as we know, is going to be perfectly accurate. There are going to be some issues in it. Some error is going to be inevitable even if you do it with high precision instruments. There are going to be some errors. So broadly speaking, there are two main types of errors. That is, one is known as random error, then the other one is known as a systematic error. As the name itself suggests, the random error can take place anywhere, anytime, even howsoever good your way of measurement is, howsoever good your instrument is. For instance, you are trying to measure the time period in an open air. Suddenly there is a gust of wind that flows through. Obviously, the pendulum's time period is going to be influenced, right? And as a result, the calculation or the time period that you're going to get for any particular oscillation or any set of oscillation is not going to be correct, right? So that's the reason we say that random error can take place anywhere. It can arise when observers estimate the last figure of any measurement using any reading, using any instrument. It can be contributed by background noise or mechanical vibrations. These are called random errors because they are completely unpredictable. These can be minimized by averaging a large number of readings. If you take very, very large number of readings, let's say for any particular measurement you take 5 to 10 to 20 readings, then if you take an average, the amount of random error is going to be minimized. So there can be some errors which may be just out of the box, so you can get rid of those. The freak results can be disregarded. When we talk about the systematic errors are not random, but they are going to be there in every measurement. It can be because of many reasons. First of all, it may be a flaw in the measurement of the instrument, using the instrument. For instance, if you are using a galvanometer and without starting off with the reading, the galvanometer reads some value. So the first thing is that you have to make it 0. You have to scale it down to 0. So that's the first thing. In the same way, for instance, if you are trying to measure, let's say, the time period using a stopwatch, the stopwatch is not scaled down to 0. In that case, it's going to produce some errors. That's going to be another thing. So systematic errors are going to be consistent because it's the way or it's the fault in the instrument or the way you're doing it. So there can be 0 error, as I mentioned. Then there is also going to be dependent upon the weather condition of a particular day. You cannot reduce it because it's going to be constant in all measurements. So you cannot reduce it by the way of averaging out. Now, taking all these things into account, if you have to measure something, if you have to measure the length of any particular quantity. So if you have a measuring tape, you can use it for relatively long lengths. You have a shorter length, you can use a measuring tape or a shorter rule. That's going to be accurate enough. Now, for instance, you are trying to measure any length, any particular point using a scale. There, as you can see on the board, there are 3 different ways you can do it. Only one is going to be correct. If you look at from this end, obviously you will find that whichever point here is matching is going to be towards on the left hand side. If you are looking at from here, then the point is going to appear on the right hand side. But the most accurate measurement is going to be there if you look at exactly from the top. When you are looking exactly from the top, that's going to give you the correct measurement. So the correct measurement is going to be looking from the top. But if you have measured all the values looking from the left or from the right or from both, in that case that's a systematic error, and you cannot remove it even while measuring from, means even while averaging out all your measurements. So the best way to measure, you place your eye perpendicular to this, and that's going to avoid the parallax errors. Okay, moving on further, there are many instruments, as I just mentioned some time back, that for instance you have a galvanometer which is not scaled down to 0, there is going to be a 0 error. So if you don't take into account the 0 error, all the measurements will have an additional amount. So the scale is not going to start from 0, instead it's going to start from some other value. So that is going to creep in into all particular measurements. So these errors happen because of adjustment or the flaw in the instrument. So in this particular case, either you have to add or subtract the values of the 0 error depending upon to which side of the 0 was the original instrument. Okay, now if you have to measure, this is a very important thing. Please understand up to what level of measurement you can do with a particular instrument. If you have to measure the length using a measuring tape, the range of measurement is going to be up to from 0 to 5 meters, and at the most you can go up to 2.1 centimeters. You cannot go beyond this. That is up to 1 millimeter that you can measure. And the same goes for the case of meter rule. In the case of meter rule, at the most you can measure up to an accuracy of 0.1 centimeters. That is 1 millimeter. Then there are certain instruments which are calibrated to measure small values. For instance, you have a Vernier Caliber or a micrometer screw gauge. Vernier Caliber can measure from 0 to 15 centimeter, and it can go up to 0.01 centimeters. That is up to 0.1 millimeter. It can measure up to that. In the same way, if you talk about a micrometer screw gauge, it can go up to 0.01 millimeter. That is, it's even smaller. So it's one of the most precise instruments that you can use to measure the values of the lengths for small lengths. Now let's talk about the Vernier Caliber first. So this allows measurements up to 0.01 centimeter. It consists of let's try to look into the figure. So this is a Vernier Caliber that you can see. Now here, this is your main scale and this is the Vernier scale. You can see the least count. Please understand what is the least count. Least count is the minimum possible value that you can measure using any particular instrument. The least count of this is 0.1 millimeter. You cannot go beyond this. Your measurements cannot go beyond this. Okay, so here you can see that 0 to 10 are the total readings, and the number of readings you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the readings that you have. So it consists of a 9 millimeter long scale which has been divided into 10 divisions. This length is 9 millimeter and this has been divided into 10 divisions. Therefore each division has a value, each thickness has a value is equals to 0.1 millimeter. So you cannot go beyond 0.1 millimeters here. So the object being measured is between 2.4 and 2.5 centimeters. The second decimal that you place is the marking on the Vernier scale, which coincides with the marking on the main scale. Let's try to go back here. So if we just try to see, let's say the first division, 0 coincides with this. So there is no reading that needs to be taken into consideration. If you say the second reading coincides with any division on the main scale, in that case, that needs to be taken into account. So after 20, whatever division, let's say the third division coincides of the main scale, and here the second division coincides. So second division here is going to be given by 0.1. So 0.1 comes from here. From here, if I have to say 20, because this is going to be in centimeters, the main scale is going to be measured in centimeters. So if I am writing down in centimeters, so it's going to be 21, because each division or third division is same. So it's 23.1. 23.01, because the measurement is in centimeters, the net measurement is in centimeters, so it's going to be 23.01 centimeters. Okay, now let's try to understand it in much more detail. Let's say, So what we have here, so the object being measured is here, right? Now what's the reading that is coinciding? You see that this is the reading that is coinciding. Now further, the object being measured is between 2.4 and 2.5. How do we know that? This is the starting point up to which has been there, and this is 2.5, this is 2.4. So the object length lies between 2.4 and 2.5, because obviously you have put the object till this particular point. This is the thickness of the object that we are referring to. So the object length is lying between 2.4 and 2.5. The starting point of the vernier is between 2.4 and 2.5. And what is the coinciding reading? The coinciding reading is here. So which is the reading that is coinciding? First, second, third, fourth, fifth. So fifth, sixth, seventh, eighth. Eighth reading on the vernier scale is coinciding. So what will we say? It's going to be 0.08 centimeters and it's going to be 2.48. Why 2.48? Because as I said, it's lying between 2.4 and 2.5 on the main scale. And what is the vernier scale reading? Is the 8th division, so 0.08 centimeters or 0.8 millimeters it is. You cannot add centimeters to millimeter directly. You have to bring it down to centimeters. So it's going to be 2.48 centimeters. So this is how you need to measure. Now here in this particular case, the reading is showing to be 3.15 centimeters. The instrument in this particular case, so when we are saying this, so here you have placed this ball, these are the outside jaws that you have. So you can either measure the thickness, inside thickness, if you have, let's say, a open bowl, so you can just put the inside jaws there. If you have to measure the outside thing, then you place it between the outside jaws. Okay, the depth can be measured using this. Okay, now the instrument has inside jaws like we did in the previous case. We can measure in this particular case as well. So here the coinciding division is here. So that's the reason you get the 5th division, so 0.05, and 3.1 because it's just between 3.1 and 3.2. So the net reading is going to be 3.15 centimeters. Now is a further more precise instrument. So this is known as a screw gauge. You can use it to measure the diameter of fine wires, very fine wires, thickness of paper and small lengths. So in this particular case, you have two main things. You have a main scale and you have a circular scale. There are 50 divisions on the thimble which can move. One complete turn of the thimble moves a spindle, that is so this is what we have. So you can see that once you move this, if you move this by one unit, that's going to cover the complete page. So there are 50 divisions on the thimble. One complete turn of the thimble moves the spindle by 0.50. So you can see that this has 50 divisions, so this can move. So this has 50 divisions and one of it gives you 0.50. One complete turn moves this spindle, this here moves by 0.50 millimeters. Each division on the circular scale which can move is 0.01 millimeters. Now there are a few precautions which you need to keep. You shouldn't be tightening it up. You shouldn't be moving it too tight. That is, this shouldn't be moved too tight. Modern micrometrists have a lasher to avoid this, but you shouldn't be doing that. Clean the ends of the anvil and spindle before making a measurement. That is, you should clean these ends before you try to do any kind of measurement. Any dirt could affect the reading. Check for zero error. That is, when you don't place anything, you just move it and tighten it up and see that it's the zero that coincides with the zero of the circular scale. The reading should be 0, but if it is common to find, it may be possible that there may be some zero error. So you just measure it whether it's a positive zero error or a negative zero error. Positive zero error or negative zero error, how do you understand? That is, if the zero lies below, that is the negative. If it's lying above, it's a positive. So positive has to be subtracted, negative has to be added up. Okay. Now, if we move on to the case of time, like we have measuring instruments for the case of length. In the same way, if you have to measure it in time, So time is going to be measured in years, months, days, hours, minutes, seconds. Then you have microsecond, femtosecond, nanosecond, and so on. There are many systems. The SI system of time, generally broadly we use time in seconds. So we are always going to differ in terms of seconds. So the clocks use a process which depends on a regularly repeating motion, which termed as oscillation. Oscillation basically means that it is going to repeat after a certain interval of time. So that is what is known as the measurement of the time. Then if you move on further, the oscillation of a simple pendulum is an example of a regularly repeating motion that you have. The time for one complete oscillation is referred to as the period of the oscillation. How does it measure? It keeps on rotating. The bob of the pendulum keeps on rotating. As a result of that, you can measure the time period of it. The pendulum clock, if you have to say, so the pendulum clock measures long intervals of time. It measures in hours, minutes, seconds. In this particular case, this is a kind of thing, so a mass is allowed to fall, and under the gravitational potential energy, it keeps on rotating. This is what results into the motion. In the same way, you have watches. Watches are used for measuring long intervals of time. They depend on the vibration of the quartz crystals that are kept inside, which are known as automatic watches that we have these days. Energy from the battery that is there within the watches helps it to keep on moving. Then you have the stopwatch. Stopwatch is utilized for measuring very small intervals of time. So there are digital stopwatch, you have an analog stopwatch. Both measure small intervals of time. It can measure up to 0.01 seconds. Analog stopwatches measure time in the intervals of 0.1 seconds. So this is what we have. If we try to understand about the errors, if you have a digital stopwatch, it can measure up to 0.01 second, but there is also going to be reaction time that is also there, so that also takes into consideration. So an analog stopwatch is therefore going to be very useful. So hopefully you understood till this point. We'll try to do some numericals in the next part. In this part, we learned about how exactly the errors creep in. What are the different types of errors? That is the random error and the systematic error. So how exactly they are different and how exactly they creep in our system of measurements. We found out the different cases of measuring the length using different apparatus. For example, a meter scale, a Vernier caliber, and a screw gauge. Similarly, we have tried defining the measurement of time using two methods. Now we'll proceed further into the measurement of time and going further into the errors and the accuracy part. So stay tuned for more.